Okay, so we tried the 2 by 2 case. We sort of want to try the 3 by 3 case as well, but there's a lot more possibilities in 3 by 3 case, so you don't want to just kind of get lost in them. So we're trying things and we're looking at things. And I mean, the idea of this diagonal, non-diagonal thing is very interesting. Okay, so that's something we should probably investigate a bit further. So one of the things I tried to do was try to sort of quantitatively distinguish between a diagonal and a non-diagonal. Okay, so for example, I started labeling these squares. So I would label the top square 0, 0. I would label the second square 0, 1. The third square 1, 0. And the last square 1, 1. Okay. So if I did that, then one thing I noticed the difference between a diagonal position and a non-diagonal position is that the diagonal positions sort of, there's an even number of ones. Okay. So in this case, there's 2 ones, and there's 2 ones in either case. Okay. You know, more generally, there's an even number. And then when it's not diagonal, there's an odd number. Okay. So, so that's why you can't say not 2, because if it was not 2, it could be 0, so it's odd. Okay, so there's 1 1 between the vertical here, and there's 3 1s here. There's 1 1s across, and there's 3 1s across. Okay, so how can we sort of summarize that? So when you look at it, so when you have picked 2 pieces, you're basically picking 2 starting positions, is picking 2 of these numbers, right? And then when you look at those numbers, well, how can you change them? Well, you can add 1 to one of the values per move. Okay, so if you define something like the total as like the total of 2 numbers just to be the sum of all the numbers, so the total of this starting position is equal to 0 plus 0 plus 0 plus 1, right? So we're trying to define an invariant, I guess. So we just define the invariant to be the sum of all the numbers that occur. And then we notice that, you know, one of the things that happens is every time you move it, it has to go from even to odd, okay, or odd to even, because when you move it, you have to add 1 to one of the places every move. So every move will be a shift from, so this is odd. If you move it, see if it's 0, 0, 0, 1, that's this position, okay? If you move it, you can either move this one down to 1, 1, okay? Which gives you 1 plus 1, which is even, okay? Or you can move the other one down to 1, 0, 1, 1, which is, is 1, 0, 0, 1, okay, which is still 1 plus 1, which is 2, which is even. So every time it's odd, it has to go to even. That's the same as saying every time it's non-diagonal, it has to go to diagonal. Okay? And so there has to be, for this to all link up in one long chain, there has to be basically the same number of odds and evens, maybe up to difference of 1 or 2. 1. Okay? So, and this idea actually generalizes, and it doesn't even need to be tweaked very much. It actually generalizes almost exactly. See, like we tried it on the 3 by 3 case. So you have a 3 by 3, and you label all the squares like 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Okay, and whatever starting configuration you take, okay, say you take 0, 0, and 0, 1, right? So the only way to move is to increase this one by 1, or increase that one by 1, or increase this one by 1, right? In another case, so this starts off as odd, because it's an odd number of 1s, and it has to go to even, okay? So now we've defined something where the chain will have to be odd, even, odd, even. Okay, so then it's a matter of actually showing that the number of odd and the number of evens are not off by 1. Okay, but look, how many odds are there? So the number of ways of getting an odd starting position, right, is to basically pick an even and an odd square together. So there's how many even squares? There's 5 even squares and 4 odd squares. So there's 20 ways to pick. And that's like with the white first. You could pick the black first, and then it's another 20. Okay, that's 40. And then what remains, there should be 32 that remains, because there should be 9 times 8 equals 72 ways of starting this game. And so, of configuration, sorry. And then, how do you get the 32? Well, you either pick 2 odds or 2 evens, right? And the order matters because it's a white and a black. So out of the 5 evens, picking 2 is 5 times 4 in order, so it's 20. And out of the 4 odds, picking 2 in order is 12, right? 4 times 3. So 32 and 40 are actually off by 8. It's too much. So that actually proves that it works for the 3x3 case, okay? And I think this should give you enough confidence to actually finish it for the 8x8 case. And also, it also solves part 2 of the problem as well. This method is nice enough to actually solve to the second part, because the second part asks you something like, what if you didn't have to do the moves in you didn't have to do the moves in black white order. You could just do multiple moves with white and then followed by multiple moves with black. But the point is, no matter who moves, black or white moves, it still goes to odd to even. Okay? So hopefully that makes sense. And good luck in the tournament.